Hi everyone, welcome back to block 2 of the semester 1 for linear programming. I hope that you are all well and ready for the new block. As I'm going to give a little background on what we have covered so far, and then from there we can build on to simplex, which we were supposed to start with. Okay, so you remember that the objective of linear programming is to obtain an optimal solution of a system of the system of equation if you are given. So again, remember that linear programming deals with the problem of minimizing or maximizing a linear objective function in the presence of a system of linear inequalities. So linear objective function represent cost or profit. So you are either minimizing cost or maximizing profit in that instance. Right, or you're trying to maximize revenue or minimizing cost of the firm. Right, so a larger and a complex problem that student can solve in a definite amount of time using the simplex method. So later when you have a multivariable linear programming, we might need to use other method, i.e. simplex method or big M method to solve it. So in the first part of this lecture, we study a graphical method for solving a linear programming problem. And then this method is helpful in choosing the best feasible point among many possible feasible points. In the next part, we will study the simplex method, which is useful in solving linear programming with more than 2 variables. A point minimizing or maximizing the objective function and satisfying the set of linear constraints is called a feasible point. And in this course, you must understand few things, and I listed them here for you to just make sure that you remember. So when you are going through the notes, just make sure that you understand these things and you pay attention and ensuring that you understand it. By the end of this course, you should be able to present different formulation of linear programming problem. You should be able to formulate a linear programming problem from a worded problem. So we will give you a statement and you should be able to actually extract the linear programming in a standard form and solve it. Right. So you should be able to solve the linear programming problem graphically. I did this extensively for various forms of linear programming, i.e. a linear programming with a unique solution, a linear programming with a bounded solution, a linear programming without a solution, and a linear programming with unbounded and with a solution, that was for minimization, and unbounded without a solution, that was for maximization. So just remember those things. Present linear programming algorithm that will be used in this course. So we should be able to understand, not necessarily present it, but understand how do we actually formulate an algorithm, or how do we go about following the algorithm to solve a linear programming problem. Right, you should be able to solve a linear programming problem using simplex methods, solve a linear programming at last, then solve a linear programming problem using the big M methods. Right, so simple example of a linear programming, for example, so a linear programming problem is concerned with solving a very special type of problem, one in which all relation among the variables are linear. So you should make sure that your objective function and your constraints are all linear. Right, both in constraint and the function to be optimized. A linear programming problem is an optimization problem which can be written in the standard form as, so we could write a minimize here. So we're minimizing, this should be our objective function subject to our constraint. Here I put equality, but you could put inequalities depending on whether different inequalities. And I did explain here that the vector inequality x greater than 0 means that each component of x is non-negative. So you don't deal with the non-negative things when you are solving linear programming problem. In above problems, xt is called an objective function, so this part is called an objective function, which in this case is to minimize, and ab are called a set of constraints. This problem is an example of a minimization. We can also maximize by replacing, you check maximize and you put where there is minimize and you can maximize. And in place of this, we can write the inequality such as this being greater or being less in the above LP problem. The purpose of this section is to formulate linear programming problem and illustrate the application of linear programming method graphically. Here are 4 important characteristics of linear programming problem that must be considered. So you need to remember, as I have already taught this in class, which I hope that you still remember it. You had to be able to identify your decision variable. So you have, when you're given a linear programming statement, you need to define what is your decision variables. You need then to define your objective function, whether you're maximizing or minimizing, and then your constraint, what is your limitations. Remember, your optimal solution must satisfy your objective function and must satisfy your constraint. 2 things which are very important, right? And then we have a non-negativity constraint, i.e. remember that we say the x1 and the x2 can never be negative. So always remember that. So both the objective function and the constraint of a linear programming problem are linear function of x1 and x2, or whichever letters you choose. So you could choose, when you are choosing your decision variable, you don't necessarily have to choose x1 and x2. You could choose any letters, Siabonga and non-tobacco. So that even name of people, it works. Right, so example of LP formulation. So we'll start by looking at a simple example. This is just a recap of what we have done before, and then I'll go. So I will be moving a little bit fast when I'm discussing this part. So you have a store produce and sell pants and jacket. The price of a pair of pants is 60 Rand, while the price of a jacket is 50 Rand. Every pair of pants require 1 meter square of cotton and 4 meters square of polyester, which every jacket requires 2 meters of cotton and 2 meters of polyester. The store can buy 1,000 meters square of cotton and 1,600 meters square of polyester. So this is, you see that this is the maximum amount you can have for a cotton, and this is amount you can have for polyester. What is the number of pants and jackets that the store should produce and sell each month in order to maximize its revenue? So this problem can be formulated as the following linear programming problem. First, you decide what is your decision variable. Let x1 be the number of pants and x2 be the number of jackets. The main goal of the store is to maximize its revenue. So the objective function is stated as follows. So you know that you take the price times the quantity. So 60 times x1, which is the number of pants, and 50 times x2, which is the number of your jackets. Right. Subject to what then? What are you going? So remember that you say to make cotton, what do we want? We require 1 meter of cottons, so that's going to be 1x1 plus what? Plus 2, so 2 what? While every jacket requires 2 meters of cotton, so you summing up amount of cotton you want, 1x1 plus 2x2, it should equal to 1,000. Similarly, you're going to sum another one to be 4x1 for polyester, the amount of what? The amount of a jacket require. Remember that the cotton and 4 meters of polyester, while jacket require 2 meters. So this is going to be a 4x1 plus a 2x2 to get 1,600. So, and then you have your non-negativity constraint, where x1 is the number of pants and in hundreds produced per month, and x2 is the number of jacket in hundreds produced per month. See that you obtain the following solution. So last time you can plot this graphically and try to find out where this is maximized, right? Now, if you know this is maximized, you could rewrite this by making x2 the subject, and you get your iso profit line. Then you, after plotting your constraint region, which gives you a feasible region, i.e. this is gonna shade downward, this as well, you're gonna be shading downward, and then you plot your iso profit and find where it reaches the maximum. So you such that your objective function is satisfied and your constraints are satisfied. Right, now if you do that, so remember that in the lab we started using Mopad, so you could actually just use Mopad, or you should do actually this manually for practice purposes. Now if you plot it, you should see that your feasible region should look like this, and then you should make sure that you get x1 to be 200. What you should find that at this point, x1 is 200 and x2 is 400, and you get that z is 32,000. So that is the point. So this point is a point which you maximize your objective function and it satisfied your constraint. So these are both your constraint. So this is one of them, and this is the other one. So make sure that you can plot it. Second, so that was a weighted problem you are expected to be able to formulate. So two things you expect to be able to do from this one. You should be able to formulate this and be able to plot this and find the optimal solution, right? i.e. as we did in class. Okay, so example 2, graphical method. So in this one, you are not given a weighted problem, you are rather given a stated normal problem, and you need to be able to solve it. In this instance, we are maximizing z equals 3x1 plus 2x2 subjected to this, right? So again, you plot this and you see, you should be able to see, you should be able to plot to get something like this. If you plot it, and then your objective function, again, you're maximizing, so you make x2 the subject and formulate your isoprofit, which it rise up to that, and you see that at this point, your feasible region is this shaded region, and this is the maximum point, which you should get it to be 180. So do this without looking at the graph and try to solve them and make sure that you can get them, right? Okay, right. So now equation 3 is another example where a university professor sometime engaged in a business to make a little extra cash. So, you know, now COVID-19 is making life difficult. So professors have to resort in making some money somehow. So, well, how does he does? Professor Snap and his family run a business that produce and sell dairy product from milk of the family cow. The cows are Daisy, Emertude, and Florence. Together, the 3 cows produce 22 gallons of milk and each week, and Snap and his family turn the milk into ice cream and butter that they then sell at the farmer market each Saturday morning. The butter making process requires 2 gallons of milk to produce and 1 kilogram of butter, and 3 gallons of milk to make 1 gallon of ice cream. Professor Snap owns a huge refrigerator that can store practically unlimited amount of butter, but his freezer can hold at most 6 gallons of ice cream. Snap family has at most 6 hours per week in total to spend on manufacturing their delicious product. 1 hour of work is needed to produce either 4 gallons of ice cream or 1 kilogram of butter. Any fraction of 1 hour is needed to produce the corresponding fraction of product. Right. So Professor Snap product have a greater reputation, and he always sells everything he produces. He set the price to ensure a profit of 5 rand per gallon of ice cream and 4 per gallon of butter. He would like to figure out how much ice cream and butter he should produce to maximize his profit. So, hey, student, you need to help the professor make a living, you know? Life times are hard, right? So from here already, you see that he's making what, 5 rand per gallon of ice cream. So you just make your decision variable to be x1 for ice cream and x2 for butter. So it should be 5. So if x1 is ice cream and x2 is butter, then you should get that you need to maximize 5x1 plus 4x2. Right. Now, you should see that 1 hour of work is needed to produce either 4 gallons of ice cream or 1 kilogram of butter. So it's 1 to 4. So if you are making one butter, you should be making 0.25 of ice cream, and that should be what? That should be Snap family has at most 6 hours per week in total to spend on manufacturing their delicious product. So and then you should know that, but his freezer can hold at most 6 gallons of ice cream. So this then it means that your x1 should be strictly less than 6. You see that, and then you see that this one, the sum of this should be less than 6. And then again, you see that it's required to butter making actually require 2 gallons of milk. So that's why there's 2 here. And then and 3 gallons of milk for ice cream. That's why we have a 3 here. And then together the 3 cows produce 22 gallons of milk. So that's the amount of milk you actually get in total amount of milk. Right, again, if you plot this and you solve for the optimal, you should get that x1 is 4 and x2 is 5, and i.e. this optimal solution is obtained when x1 is 4 and x2 is 5 and z is equal to 40. You are expected to show all your steps in the test or in the exam. So it should look like this and you should get that point. Sure. Right, example 4. In example 4, a student, so this is like you going to Mampela every day, and Mampela is being very nice to you, or you're going to Lemon Zest. So the students usually purchase a snack every day from a small store close to her university. The store offers 2 choices of food, brownies and chocolate ice cream. 1 brownies costs 2 rand, and 1 scoop of chocolate ice cream costs 1 rand. The student has purchased her snacks from the same store each day for many years now. You know, when you are repeating so many times at best and you're just relying on Mampela to feed you. I'm joking. No one is joking. You should be fine. So the owner of the store allows her to purchase a fraction of the product if she wishes. The student knows that each brownies contains 4 ounces of chocolate and 3 ounces of sugar, while each scoop of chocolate ice cream contains 3 ounces of chocolate and 2 ounces of sugar. The student has also decided that she needs at least 8 ounces of chocolate and 11 ounces of sugar per snack. She wants to find the amount of each product that she should buy to meet her requirement by minimizing the cost. So in this instance, we are trying to minimize the cost. So you formulate your LP problem. The student needs to minimize the cost. The solution should be as follows. So what do we know? What is our decision variable? So our decision variable, we have chocolate and so how many the student know that each brownie contains 4 ounces of sugar or ounce of chocolate and 3 ounces of sugar, right? And then the student has also decided that she needs at least 8 ounces of chocolate. So if you are summing chocolate, you should get that, right? So it's going to be 4x1 plus 3x2 is greater or equal. So at least, so this at least signifies that that's greater or equal to 8, right? Similarly, if you are talking about this, you need 3 ounces of sugar and 2 ounces of sugar in case of what? So sugar requirement is 3 and 2. So that's why 3 and 2. And then and 11 as well. It's at least 11 ounces of sugar is what you require. So this is chocolate requirement and this is sugar requirement, and you should get that, right? Now, again, you should get a non-negativity. Now, since you are minimizing, you are finding the minimum point, okay? So if you do that and you plot your area, you see that if it was a maximization, it will be unbounded because it's just all this area. But since we are minimizing, we are looking for the lowest point. And the lowest point is this point, right? So this is the point which is give us in our feasible region, the lowest point is this, and it gives us a minus 11 over 2. X1, you are making nothing, and it means that the student only should then be doing what? The student only should be buying what X2 is, right? So remember that. Number 5, I'm gonna leave this out for you. I'm gonna leave this for you to go through and try to understand if you can formulate and see that you should get this and you should get the plot of this nature. And notice that there is no intersection between these two lines, right? So there is no place where these things two are intersecting, but you should be able to figure out the feasible region, right? Again, you should try to do example 6, and then there's example 7. I put a lot of examples for you to make sure that you can do them. So try to do them. In our next session, we should be able to see this. So all these examples are for practice purposes. So you should be able to try. This is just for you to practice when you're home, and we can compare from there. Okay, so my next part is now, I want to discuss briefly, to introduce briefly a few things which are important for us when we are moving towards doing simplex. So first, we need to know some few things, which are, by the way, I have already done this part in class, that linear independency, when you talk about linear independency, you are merely referring that a set of vector S, which is stated as this, is said to be linearly independent if equality that if you take these parameters multiply by this, you should get equal to 0. It implies that all coefficients which are in R are equal to 0, right? Okay, so of course, often when you are given a definition, you might not even know what it means. But if you put numbers around it and see, let us put an example, attach numbers and see. So you are given a vector A is this, and the vector B is this, and the vector A1, A2, A3, they're this. So apply the definition of linear independent. We must show that the linear combination of vector 1, A1, A2, A3 are equal to 0, in which all coefficients alpha 1, alpha 2, and alpha 3 should be 0. Right. So you should be able to do this, and hopefully I did this in class, and I hope that you can follow. Definition 2, linear independence. So linear independence. So there is linear independence and linear dependency. A linear dependency, a set of vectors S equal to this, is said to be linear dependency if there exists a coefficient that where not all of which are 0, such that equality that hold. Again, we have an example here, and prove that. So the vector A1, A2 are linearly independent because if you take this is equal to 0, where that and that are equal. So when you take lambda 1 equal to 1, alpha 1 equal to 2, alpha 2 equal to 1, and alpha 3 equal to this. I.e., you could form a system of simultaneous equation, and you just and solve to get alphas, right? You take alpha 1 multiplied by this, alpha 2 multiplied by that, alpha 3 multiplied by that is equal to 0, and solve the simultaneous equation. Or you could do the row operation. So now remember linear equation. Consider M linear equation in n unknown, namely x1, x2 to xn. You could rewrite it in this format. Equivalently, you could write that Ax is equal to B, associated with this system of equation is the matrix that. So we could rewrite this like this or like that. We can apply elementary row operation to matrix A to get the matrix in its reduced form. An elementary row operation is nothing else but it's merely just trying to either making an upper triangle or lower triangle matrix. And I hope that you have done this in numeric, or you are likely to do it in numeric at a short future. So what does this row operation does actually? So row operation doesn't really do nothing special, but it's merely an interchanging. You can interchange any two rows such as P and U rows of a matrix. So you can interchange rows of a matrix. That's allowed as a row operation. 2, you can multiply one of its row, such as P row, by a real number alpha. So you can maybe take row 1 going to row 1 is row 1 going to a half row 1. So you could do that. Or you could say row 1 moving to row 2. So you can swap rows. Right. These are important because when you're doing simplex method, you'll see that sometimes we will actually swap rows because it makes solving our problem quicker. Remember, you're formulating a logarithm which run like a search function to find the most optimal solution or most optimal feasible solution, right? Adding one of its rows such that as U row to the beta times row. So we will see this later. A rank of a matrix, we did this already. I am glad that, and I hope you still remember this. Now, recall that in class we used row operation to find the rank of a matrix, which was useful in determining whether the system of equation is linearly dependent or linearly independent, right? This further informed the nature of the solution we can have for such system of equation. So the number of non-zero rows in the row reduced form of a matrix is called the rank of the matrix. So we denote it like this. So if you can find the number of reduced rows, that we denote it like this, and that's what a rank is. And why do we need a rank? I explained it above, and you should know that. Not that if a matrix is of the order m, so it has row m times column n, and the rank is equal to m, then A is said to be of a full rank. I.e., if your rank is equal to the number of your rows, then A is said to be a full rank. Example, find the rank of the matrix. So you're given this matrix, and we want you to be able to solve the rank. So we perform a row operation as follows, and we can obtain the rank of matrix. So we perform the following row operation. So again, I took, remember I'm trying to make the upper triangle equal to 0, so that and that, I need it to become equal to 0, right? So what am I going to do? From the above matrix, I say that row 1, all I want to do in row 1 is row 1 going to row 1 is a half row 1, we get the following. Then do another row operation as follows, row 2 is equal to row 2 minus row 1 to obtain the following. So we get that. So this one becomes a 0 and everything else, right? Then performing another row operation, so we're getting an upper triangle matrix. So if you perform another row operation, I need to get, so here, what I'm trying to perform is I'm trying to make this number 0, and then the next time I'm going to try to make this number 0, and the next time I'm going to try to make this number 0, right? So that's what this row operation do. So by doing such here, this row operation achieves 0 here. The next one, this one achieves 0 here. Therefore, P is a number of non-zero, the number of non-zero rows is equal to 2. So homework, try the following. So for you, I need you to try to do this. Try this at home and make sure, try to find the rank of the matrix. So here, the rank of the matrix is equal to 2. Now I need you to try do this as a homework. You should perform a maximum of 5 row operation, and you should get that the number of rows is equal to 2. The system of linear equation is to be consistent then. If so, when is the system of equation is saying to be consistent? If your rank of A is the same as a rank of the argumented matrix, then the system is the system has a unique solution. So if you got the rank of the matrix A, just A itself, and the matrix of A with B, which is this an argumented matrix, if such is true, then we say that the system have a unique solution. The system have infinitely many solutions if the rank of matrix A is equal to rank of that is less than number of variables. So inconsistence is if the rank of that is not equal to this, then the system has no solution. Okay, example, solve the following system of equation. So we can write the system of linear equation, so we can write this in argumented form, i.e. in this format. I can write this like this, okay? We proceed with the elementary row operation as follows. Again, we're doing the same thing. We're trying to achieve a 0 here, or we already have a 0 here. This is a lucky day for us. It's not always true, so you have to perform all the row operations. So by performing all the row operation, you see that now, you see that the number of non-zero rows, this one is non-zero because there are numbers, non-zero because of course there is that, right? We can see that one, so if you recall that this one, this part, this has what? Has, if you are looking on this, it has what? If you are only looking at that, surely it has 1 and 2 as what? As our rank. But if you are looking at it, all of it, it means there are 3 of them. So non-zero is that. If you are looking at the whole matrix, if you're only looking at matrix A, it's only this part, right? Which means this row and this row has non-zero numbers, and this row has zeros. So there are 2 non-zeros, which means the rank of A is just 2. But if you're looking at the entire thing, there are 3 rows with non-zeros, which means this is 3. So that is not equal to that the system is inconsistent and it has no solution. So that's a very simple, right? Now, so we got here, and this is a simplex method. So I want you to read up to here, and then in my next lecture, I will explain simplex method. Right, so thank you very much for watching the video. I need to encourage you that this video will be uploaded on Sakai, and it will be uploaded on YouTube, and the link will be attached to the notes, and the notes will be on Sakai as well. You should read up a simplex method before tomorrow, so when I explain tomorrow, you already have read up the simplex method introduction. Thank you very much. Stay safe and read as much as you can, and send me an email if you find a typo in my notes. And remember, the notes are not error-free, but I will try my best every time to find how to make your learning as comfortable as it can get. Thank you again. Have a wonderful time.